so let's take a quiz over what we've learned today. Question number 1, why does the equation for radar imaging have a 1/2 in it? All right, so let's go back to, it's a long ways. All right, so let's go all the way back to this equation here, which was we are going to take a radio wave and bounce it off an object. We're going to time how long does it take the radio wave to get there and then to come back. And then from that, we're going to be able to figure out the distance to that object. So it was equal to the speed of light, the total amount of time that the radar beam was traveling, and then divided by 2. So the question is, what's the 2 in there for? It's because the signal has to get there and then come back, so it's actually traveling twice the distance. So therefore, if we divide it by 2, then we get an accurate reading about how far away it is. So that was question number 1. Question number 2. The large shift in parallax of a star means that the star is what? So if you're looking at a star in January and you look at the same star in July, on the photograph, the star is going to be moving back and forth. So if you see a large shift in parallax, does that mean that the star is closer to you, or does it mean that it's further away? And so this time we're going to be using the parallax equation, which is 1 over the angle. So if we make this thing larger, then this thing gets smaller. So that means it's going to be closer to you if it has a large shift in parallax. Question number 3. The higher the temperature of a star, the brighter or dimmer the star will be. Okay, so this one has to do with the black body radiation laws. And so there was one of them that said that the brightness was proportional to T to the 4th power. So the hotter a star is, the brighter the star is going to be. And you can also figure that out from the HR diagram. So here's your main sequence stars, and down here was the temperatures. So the higher temperatures were over here. So if you go, then that means that they had the higher luminosities that went with them. All right, what is a Cepheid variable star? Okay, a Cepheid variable star, it's variable, so that's your clue. So it is a star that periodically gets brighter and then dimmer and then brighter and then dimmer again. And we can measure the rate at which they get bright and dim, the period, and then from that we can figure out how bright they are. And then from that, we can figure out how far away that they are. Number 5, use the graph of rotational speed versus luminosity to answer this question. A faster rotating galaxy has a luminosity that is brighter or dimmer than a slower rotating galaxy. Okay, so can you remember what was the graph that goes with this? Okay, so let's take a look at it. So we want the graph of the rotational speed versus luminosity of a galaxy. There we go. All right, so this one was the Tully-Fisher relationship. And so take a look at that graph right there. Okay, and what it has is luminosity is going up, and then going sideways is the rotational speed. So how fast is it going around? And then the graph is doing this. Okay, so if the rotational speed is getting greater. It's going over here. So then that means that the luminosity is getting greater. Okay, so the faster a galaxy is rotating, the greater its luminosity is going to be. Now this all comes from Kepler's laws. All right, do you remember that the greater the mass of a star, the faster a planet would go around it? All right, so the greater the mass of a galaxy, that means it's got more stars in it. If it has more stars in it, it's going to be brighter. So that's essentially where this is coming from. All right, next question. How far away can a white dwarf supernova be seen? I don't remember. All right, so let's go up here to those white dwarf supernovas. Okay, so here this one was called the Standard Candle, and so this was a star that was exploding, and then we could measure its luminosity and then use that to figure out the distance to that supernova event. So it says here that this method is not useful for distances greater than 10 to the 10th light years away. So 10 to the 10th light years. All right. Now, question number 7. Hubble's law is based on the premise that the further a galaxy is from you, it will be moving what? Okay, the further galaxies are from us, the faster they're moving away from us because of the expansion of space and time. Number 8, assume that a galaxy is moving away from us at 44 kilometers per second. How far away is it? Okay, so this time we're going to use the idea that the distance r is the speed divided by Hubble's constant, which is what number? 22. So we're going to take 44 divided by 22, so that's going to be equal to 2. And then do you remember what would be the unit? So it's going to be mega light years. So that's how far away that this particular galaxy is. 2 million light years away from us. Number 9, name one reason why Hubble's constant is important. And so we had 4 of them. All right, so if we go back up to here, reason number 1, Hubble's constant determines cosmic distances. Reason number 2, Hubble's constant determines the age of the universe. Reason number 3, Hubble's constant determines how fast the universe is expanding. And then finally, reason number 4, Hubble's constant determines the amount of mass and energy density needed in the universe to keep it from expanding. And we're going to talk more about this in a future lesson. All right, so there you go. Easy as pie. So in our next lesson, we are going to switch gears. So far, we've been talking about objects that are very, very big and using the concepts of general relativity to explain stuff. In our next lesson, we're going to be talking about things that are teeny tiny, and we're going to have to use concepts of quantum mechanics in order to explain how they work. I'll see you then.